You basically already know everything about it from a technical point of view, but the concept, that's the part that is actually new and the applications of it. So, well, I'll introduce mixed model in the GWAS setting, genomatization study setting for population structure correction. So, just quickly explain what I mean with population structure, and then we talk about how to do that with linear mixed models. And then I'll talk about various applications of linear mixed models, like testing with population structure correction. But we also saw a different one in the review paper that we read, where we basically said you can also use them to estimate heritability of a trait and all these kind of things. Well, that's the same as the slide I had up many times. So basically, you're given a bunch of SNPs and phenotypes for the same individuals, and now these phenotypes could be diseases, or they could be quantitative, and what you're trying to find is some loci in the genome, some SNPs that correlate with the phenotype, or that are associated systematically. A problem with that, or this is basically the same thing kind of as a graphical model, so we basically say we have a bunch of SNPs that regulate a phenotype, so XS, but XS might not be measured itself, but we just genotype some SNPs along the genome that are in linkage disequilibrium to the causal SNP because they are close to each other. So this is basically some sort of statistical dependence between them. And, well, there's of course a causal dependence between the regulator SNP and the phenotype. So there's basically a path that connects the genotype SNP that we're going to test and the phenotype leading to an association. But the problem, well, if we have other SNPs that are not dependent, that don't have a dependence with the causal SNP, then hopefully there's no association. So that those are, for example, SNPs that are on a completely different position in the genome, for example, a different chromosome. So there's no reason why two SNPs on two different chromosomes, in theory, should be related in any ways, because there cannot be, I mean, there's no crossover between chromosomes and stuff. So linkage disequilibrium should be 0 in theory. The problem is that the way we do these studies is that we typically do population-based sampling. And, well, basically what this means is that, well, some individuals might be closer related to others. And what basically happens is that there's some sort of population structure, which is a hidden variable, we don't know it. And it creates a dependence between the causal SNPs and all the other genome-wide SNPs, just because, yeah, I mean, if one SNP is more common in one population because of non-random mating, because you tend to mate within the population, not across the sea or whatever, then not just the causal SNP gets more frequent in that population, but also all the others, or gets a different pattern of you would observe it. For that reason, now there is some sort of a dependence, just because this population structure basically makes the causal SNP and SNPs that are not in physical linkage disequilibrium dependent, and we see it also associations to those. And, well, in a GWAS, those lead to type 1 errors or false positives. So basically what we want to do is we want to take this population structure into account. Basically, if you're familiar with graphical models, if you condition on such a V structure, then the dependence goes away, because every correlation between this variable and this variable is explained by this one. And that's kind of what we're trying to do in a linear mixed model, in order to get rid of these spurious associations. Well, there are several challenges. One is that study sizes are large, so you want efficient algorithms. And, well, the reality is actually that typically there's not just one causal SNP, but it's many, and you can basically view these other causal SNPs. Basically, they even amplify this effect of having a correlation between this SNP and the phenotype. Because basically, if you view, basically, these are all kind of, say samples from this population distribution, as well as this, then basically, if you add up all little contributions from this, you get more contribution of the population structure observable in the phenotype. So, kind of, we want to model this. And the other thing is also, in a GWAS, everything that we don't include in the model, if you go to this linear model view, has to be explained by random noise. So, kind of our sigma, our noise variance sucks up everything that we don't model. Which is fine as long as everything is uncorrelated, because that's kind of a model assumption. But as soon as there's a correlation, the model is just misspecified. We get false positives. The other thing is, if we actually model these things, so say we would introduce one covariate for each causal SNP, then we would also gain more power, just because the signal to noise ratio would go higher, because the noise variance could go smaller, because everything is already accounted for. All the variance that is, so if the true model is some sum over some causal SNPs times the betas of those, plus, say plus the SNP that we're testing, plus noise. Then if you don't include this part, you have to basically suck up all these things here, right? And but if we actually include those into the model, then the variance of this variable can go down, because it doesn't have to include the variance in y due to these. And so the actual signal part, assuming that it stays constant, so the signal to noise ratio goes up. But more to this later again. And, well, another task or challenge is, for example, if we have multiple weak effects, for example, rare SNPs, we've already said, because they are so rare, the amount of variance that they can actually explain in the population is very small. So we also have very low power to detect these, and we also want to look at ways to model these, for example, by aggregating their contributions to the phenotypic variance, and mixed models also used for that. Okay, so, well, if we have SNPs and the phenotype, what we test, typically a linear model, right, where we have the SNP times a weight, distributed according to this normal distribution where this is the mean, so SNP times the weight, disregarding covariates for now. And, well, a covariance, which is just an identity matrix times the noise variance. So individuals are assumed to be independent, and then we, for example, do a likelihood ratio test or a Z test. I mean, we looked at several tests before. Now, as I said, if you have population structure, what happens is that basically you get kind of clusters in the data, where within a cluster you're more similar than between clusters, and the same is also true for the phenotype. Just because within the cluster you also share all the causal variance, so if you just aggregate over these causal variance, then you also aggregate over similarities in the phenotype. Or doesn't just have to be causal variance. It could also be that if you come from one place, someone else, a different group of people comes from a different place, there might also be shared environment within a population. Which also, so one population is close to a nuclear power plant, the other one is not, then you might see that in the phenotype. Random example. Well, there's not just population structure, there's also family structures. So basically within families, there is the ways that things are inherited are completely different than between, if you look at random samples from a population. For example, brothers or siblings have about 50% of their genome or of their mutations shared, while I don't know what's the expectation for two random samples. Depends on the distance between the populations. Or, well, there's this term cryptic relatedness, which is, in my opinion, just very, I think it means the same as family structure, basically. It's just that families are typically known and cryptic relatedness are probably from, like, I say you have a second cousin somewhere that you don't actually know is your second cousin, something like that. And, well, what the model basically does, it assumes that if you say you have the phenotypic values between two people and you measure them over and over again, it assumes that they are independent, while population structure and relatedness actually create a dependence, because if you sample the phenotypes between people from the same population over and over again, they tend to be more similar than if you sample them from different populations. So there's basically the likelihood model that you assume, and actually the data don't match, and there's a model mismatch problem, and that creates false positives. So, and, well, how does this look actually in a GWAS? So this is a GWAS of Crohn's disease or inflammatory bowel disease, and just uses a linear regression and a likelihood ratio test. So the very simple thing that we studied in the beginning. And if we now look at a histogram of the p-values that we get, they're very far from anything that looks like uniform. And, well, the QQ plot of the theoretical null distribution versus the observed p-value distribution, it does not follow the diagonal. So these QQ plots, you see them very often actually in the when you compare distributions. For example, in GWAS, what one typically compares is the theoretical null distribution of a p-value, which is a uniform distribution. So you basically plot all the quantiles of your observed distribution of p-values here versus all the quantiles of the theoretical null distribution. And in this case, it would be log p-values. So you basically take uniform values, you take the log of those, and then you plot them against each other. And if the quantiles match, right, then you should see a straight line. Then they should basically be the same. But if the quantiles don't match, you get a deviation in one or the other direction. And you can also basically, based on random sampling, which depends on the sample size and on the number of p-values that you look at, you can also get some error bars that you basically think, okay, if it's within these error bars, this is just random variation, but if it goes far outside, then you either have damn lot of signal, but assuming that actually not all the genome is causal, we can assume that most of these are spurious associations, so false positives. Right. And this is also this lambda factor that we said, which is basically the mean of the median of the theoretical distribution over the median of the observed. No, it's the other way around. The median of the observed distribution over the median of the theoretical, and that's also here on log 10 p-values. That's a 1.4 in this case. Which, if they matched up, if they were the same, because it's a ratio, if you plug in twice the same value, you should get a 1. Okay, so how do we correct for this? Well, one simple way we've already talked about it. I just reiterate this just for completeness. So say we have our genomic control factor, so which is basically, as I said, the median of our test statistic over the median of the theoretical distribution of that test statistic, which for the likelihood ratio test would be a chi-square distribution. Well, it tells you whether you have inflation or deflation. And, well, a simple way to correct for this in order to match this distribution is just to take all the test statistic and divide it by this lambda. And then, by definition, you would get a lambda of 1 afterwards, right? It's a very crude way to correct, but it's very simple. And, well, it's what people also do a lot of in practice. And it's applicable to, well, with any kind of method because it's so, right? You just need p-values for doing that. The problem is, I mean, you only match one single quantile of this distribution. Only the median is being matched. So you know that the median matches now the true one, or the theoretical one. But the others, of course, don't match up. And as a consequence, this is extremely conservative because it completely ignores any kind of data. More reasonable way to do this by using a linear mixed model. And, well, the linear mixed models work as follows. So basically, you start off with the linear regression model, and then you introduce a covariance matrix or a kernel matrix K that kind of reflects this population structure. So basically, it's a positive definite matrix. It's a covariance matrix. You say that, well, you define it in such a way that people who are closer related to each other have larger covariance than people are not so close in population structure, or not so closely related. How to do that?
This is called like the kinship matrix in that paper, right?
Yes, that's the kinship matrix in that paper. So, and, well, how can we get this? We can just take SNPs. And basically, if we just take SNPs, and we look, for example, we just compute just a empirical covariance matrix from those SNPs. So it's just 1 over the number of SNPs that we have times sum over, well, say it's k I j. Oh no, it's just let's do it for the whole k. We can just take sum over little s equals 1 to large s, so all the SNPs, xs minus, well, mean of xs transpose, or so it's just an empirical covariance matrix. And, well, what this will give us is basically if you have many SNPs that are, if you look at two related individuals, for them, most of the SNPs will be the same. So if you assume that the SNP, for example, would be in the simplest case binary, they are not, but then basically you would just count the number of shared mutations between two people. And of course, you share more mutations if, for example, if that mutation was in a common ancestor, then you have all the mutations that come from your common ancestors in common with those people. Yeah.
Between two different individuals?
No, this is now the whole matrix. That's now for, these are now vectors, so it's for the whole, it's an n by n matrix now. Yeah. So this is, each of those SNPs is an n by 1 vector. N is the number of individuals, and S is the number of SNPs. So if you're basically measuring covariance for each pair of individuals over an empirical covariance measured over SNP many variables, right? So you basically have SNP, like for each SNP you basically have one sample kind of from this population structure for those two individuals.
Basically for every individual, for every pair of individuals, you take how close they are. I mean,
exactly.
If they have a large covariance,
right.
They're pretty close.
Right. So basically, if you come from the same population, then you have more SNPs in common, and if you're from a different population or from the same family. And so basically, well, there are also other measures, for example, kinship coefficients. I mean, basically, this is an estimate of a kinship matrix. So kinship matrix is a matrix that tells you something about the kinship between you and someone else. That's what a kinship matrix does. And there are several ways. I mean, there's identity by descent coefficients that just look at the family history. So basically, that's an identity by descent coefficient would tell you the expected fraction of genome or shared with some other person. That's given by your identity by descent coefficient. The identity by state measures basically, well, what is observed. So that doesn't look at expectations. It looks at actually what is observed. So what we computed here could be interpreted as an identity by state measure because we use real SNPs. Or I mean, this is a covariance matrix. And well, what these models now do is they basically say, okay, population structure follows a Gaussian distribution, a multivariate Gaussian distribution with this k. Now we sample a random effect from a Gaussian distribution which has zero mean and covariance proportionate to this k times some scalar. And well, if we want to account for that in the study, we basically add it as kind of as a covariate, right? So it's basically this random effect, so-called random effect U, tells us basically it's basically a proportion of the phenotype that is due to population structure. It's some contribution of population structure to the phenotype. Well, and the phenotype is then just the sum of the SNP and this U. Of course, well, this is a matrix. This is something that is not known. So we don't just look at a single realization of it, but we look at the whole distribution, which is, as I said, given by this Gaussian distribution here. And the way, how do we look at all values? It's basically by integrating over this distribution here, this Gaussian distribution. And it turns out that if you do this integral, it's an integral. This is can again use the formula for a Gaussian convolution here. It's what happens is that just this k now appears. So the u goes away after we integrate it over it. And instead, this k appears in the covariance of the model. And that is typically what the linear mixed model that people look at if they do genome-wide association studies. They have this k times sigma squared g, which is a genetic variance, and a noise variance times the identity. So there's the noise is that is in addition to the population structure is supposed to be is assumed independent. Then you have basically some population component which is dependent between individuals, and you have the model that you're testing. Well, empirically this works really well. The problem is now, well, the way it works is basically, we said the linear regression model had a model mismatch between the data and actually the model, as it assumed that individuals were independent. Now it basically takes this global covariance between the covariance between the phenotypes due to population structure into account. So it adjusts the data based on this population structure estimate from these SNPs here. The problem is now that if we do this is much more expensive than a linear regression. But yeah.
Could you please explain again how exactly the kinship matrix contributes to the phenotype? I mean, if you write down the linear regression equation.
Yes.
So we have x times
Well, I mean, it's basically, you can think of it like that. You basically have x plus beta plus some effect that is due to population structure.
Okay.
Yeah? But then you don't take just a single sample from this. I mean, you kind of define this distribution of the population structure, right? Because this is just some variable that reflects the covariation due to population structure. So you have a distribution over it. So you have basically an additive model between the SNP effect and this population structure variable.
So do you have to estimate the coefficient for this effect? Like, do you have to multiply the u by something? Or
Well, okay, so the way I wrote it, basically the u is the effect. So it's basically, this is now the random variable. That is now an effect. This is the part that you, in theory, would have to estimate, but in order to get rid of this the estimation step, you use Gaussian integration. You basically take the whole distribution into account instead of just one single realization. And mathematically, it turns out that basically the u completely disappears, and instead the covariance of the likelihood changes.
do you example from a Gaussian that has what property?
It's a Gaussian that is assumed to be zero mean and have covariance equal to the population structure. And then you, well, I mean, that is, the likelihood is you also see this often with an E, where the E stands for environmental noise, to contrast it to the genetic noise. And well, this is proportional now to. No, leave out the normalization constant. So instead of taking the sum of squares, which would basically correspond to only having the identity here, you now take basically the inverse of this n by n matrix into account. So you reweight those pairwise similarities, or the sum of squares based on this covariance structure. So
u is a vector, right?
Y is a vector. This u is a vector. Yes, yes, it's a vector. It's n by one vector. So it's for
so kind of each component of that vector is something that you add to the beta times
x. Right.
the
Exactly.
x of that individual.
Mhm.
Right. Okay.
Exactly.
So it's something that compensates.
For population. It's basically you can view it as everything. I mean, because the model is so simplistic, we only look at one single SNP. It is basically everything that is shared between any pair of individuals based on population structure.
Yeah, no, I was trying to figure out what do the individual components of U actually mean.
Yes, it's the, well, U is basically the part of Y due to population structure. It's if you write Y as a sum, it's basically Y equals X beta plus U plus noise.
Yeah. So basically, U sub I would be the effect for individual I that is explained by the population.
Exactly. Mm-hmm. Okay, so the problem with this is now that instead of just computing a sum of squares, we always have to do this. Basically, have to find these parameters sigma g and sigma e, and we have to take an inverse of this matrix, which is an n by n matrix. I mean, if you do that once, it's not a problem, but if you do that a million times because we want to do a million tests, then this is problematic. So, and also the optimization problem in sigma g and sigma e is not an easy one. So it's not jointly convex. So if you have a combination of parameters, it's not easy to check whether this is the global optimum, and it's also not easy to get there. Right. But the way around this is basically, now we are basically going to this problem of this non-convexity, because we have an optimization problem in two parameters now. So beta is the easy part. Once we have these two, beta is easy, because that is we can just write down the maximum likelihood estimator given sigma g and sigma squared e by taking the derivative and then solving it the usual way. But if we do a simple change of variables, then it turns out that we can basically get rid of one of these parameters. If we introduce a new parameter that is the ratio of the two, include it here, and then pull out basically sigma squared g. So if you take the ratio, place it here, then if you multiply sigma squared g back in here, because this is sigma squared over sigma squared g, you just get sigma squared back, right? So this is the same as this. And the nice thing of this is now that given the value of delta, the maximum likelihood estimates of beta and of sigma squared g follow in closed form. And they follow basically as, they look very similar to the typical mean and variance estimates of a Gaussian, the maximum likelihood estimate. So sigma squared g will be something like 1 over n times the residual squared after. And well, beta looks very close to the maximum likelihood estimator in the linear regression.
So you just choose a delta?
You choose a delta, but the nice thing is now that we only have a one-dimensional optimization problem. So we can repeat that, choose one, everything else falls out. Choose one, everything else falls out given this one. And then basically we take, because it's only one-dimensional, we don't care whether it's non-convex. We can just basically follow the line and go to the optimum of that.
So why don't we just choose a sigma e squared?
If we choose a sigma e squared, we also need a sigma squared g. So you basically have to do that now on a grid. Optimization on a grid of parameters. You cannot write the maximum value of sigma squared g given a sigma squared e and vice versa. But given a delta, you can write down analytically the maximum likelihood value of sigma squared g. Well, you can try the math, and you will see that that you cannot solve it. I mean, that's the problem. You cannot solve for it. But for this in this form, given a delta, you can solve for this and this parameter very easily. And that's probably a good homework to do. Okay, and well, I mean, I said we can basically just try different values of this, and then just take the max over the whole likelihood if we plug in the optimal values for the others. But I mean, there are also ways to basically run the optimizers to solve one-dimensional optimization problems, where we basically say, okay, I plug in parameter, and then my evaluation, my function evaluation, is solve for the other parameters, give me the likelihood. So plug in one value of delta, solve for beta and sigma squared g, then I get a likelihood, the maximum likelihood over beta and sigma squared g for a given value of delta. But this is still a cubic operation per snip, because it involves an inverse of this. That's the problem with that, but it took us one step further. because we got rid of one of the parameters that we cannot treat. Now we also have to get rid of this cubic operation. Well, okay, so if you look at, this is actually what I wanted to give you as homework. This is now if we compute the gradient. I mean, you should probably still do it. Well, it's just, if you write down the gradient with respect to beta, what you're ending up with is the, of the log likelihood, then what you're ending up with is the gradient of the error term, this basically sum of squares, which is this. So the normalization constant doesn't contain beta, so we don't need it. And then, well, if you take the derivative of that, or the gradient of that, we get this term here. And, well, if we solve for it, we have to set this to 0. And, well, then if we set it to 0, we can again move this part to the part, basically move that part over. There's actually a beta missing here. Sorry. If you want to write that down, there's a beta missing. I should introduce that in the slides. And if you set it to 0, so this is the correct version with a beta. Then we get this maximum likelihood estimator, which looks extremely similar to the maximum likelihood estimators of the linear regressions that we have seen so far, where instead of having x transpose x in there, we have additionally this k plus delta inverse. But we can analytically compute it. Then, well, as I said, this is very close to the linear regression thing, where instead of x transpose x, we have x transpose this part x, and then instead of x transpose y, we have x transpose this thing y. And given this, we can also solve for sigma squared g. So derivative of the log likelihood with respect to sigma squared g. There's this term here. And I don't go through it. You should just rederive it. And if we set that to 0, we can obtain the maximum likelihood solution basically as an empirical variance of the, well, this is the residual, and then again, we have this k plus delta inverse here, and times the residual. So it's basically a rebated sum of squares again. Well, the problem is that we have to calculate this k plus delta inverse all the time for different values of delta. So sigma squared g falls out because sigma squared g is just this. And beta goes away because beta is just this. Right? But all of these terms involve k plus delta I inverse. So, but if you look at the likelihood, then you can use the fact that we can take, well, that we can now use the fact that we can compute the distribution of a linear transformation. And, well, what linear transformation do we choose? Well, we replace k by its eigenvalue decomposition, where U is the matrix. It's an n by n matrix holding all the eigenvectors of k, and lambda is the diagonal matrix of the eigenvalues times U transpose to U. And now we can do a linear transformation of the whole thing. So U is an orthogonal matrix, which means that if we multiply the whole thing by U, so given the distribution of y, the distribution of U transpose y is this, where if we multiply this from left with U, so U transpose U is the identity because it's an orthogonal matrix, and from right, U transpose U is also the identity, and here we get U transpose U. So here all the parts that have a non-diagonal term go away. So this is a really simple trick, but it, yeah.
You said U is the eigenvalues
Yes, eigenvectors of K. So it's an n by n matrix where all the columns are orthogonal to each other. So U transpose U equals identity. So if you basically, if we now take this Gaussian distribution in U, you multiply U by U transpose, then we have to multiply the mean by U transpose and the covariance from both sides with U transpose, right? And because U transpose U is the identity matrix, same here, because here U comes from both sides. All the U's cancel and you're basically left with a diagonal matrix. Yeah.
So it seems like the fact of that is that you decorrelate the.
That's a way to view it. Yes, that's a way to view it.
Yeah. So could you do the same trick? I mean, like I guess the goal is to make the covariance a diagonal matrix.
Yes.
Right. So, but could you do the same thing if you multiply the covariance matrix by its inverse, for example?
By what? By
its inverse.
Say
you multiply both.
Well, you need a square root in order to make, or you don't really need a square root because the square root will give you something that is identity if you take the inverse square root. But because if you take the inverse, if you multiply it by the inverse, the problem is there's also this identity here. So if you take the inverse of K, then you basically get K inverse times K inverse plus K inverse squared, which is something complicated. And we want something that basically if we plug in new values of delta, we can easily evaluate, and basically taking the inverse of a diagonal matrix is easy. That's just inverting the elements of the matrix.
No, I was thinking of basically what you do is you somehow rotate the y's so they become uncorrelated. Right?
Yes, but it turns out that that's exactly what this matrix U does.
Yeah. So that's actually the only way to do it.
For this, no, I mean there are different ways in general to do it, but it turns out that because we want to try out different values of delta for each SNP, we have to optimize over this parameter delta. That the eigenvalues are the only matrix that have the property that basically they also cancel with the identity. You need something that is orthogonal such that you also keep the identity diagonal. And because now for every value of delta, the eigenvalues of K don't change. Right? I mean, basically still the eigenvalues are the same no matter what you plug in here. All the other ways to make a diagonal matrix, the whole covariance term, because you have to make the whole covariance term diagonal, not just this.
Exactly.
And all the other ways to do it would depend on delta. And that is why this is so nice in this case. Okay. Well, and as you said, it's basically a way to change the coordinate system. So instead of looking at the original y's, you basically look at U transpose y's, and in those there are no covariances. For that reason, we can basically do something that is a little bit more complicated, or marginally more complicated than a standard linear regression. Well, this is FastLM, some advertisement here. We have to do once still a cubic operation because we have to compute the eigenvalues, eigenvectors and eigenvalues. Well, it's exact, of course. And then for every, well, it's the memory is, of course, quadratic because we have to still compute K and then compute the spectral decomposition. But the runtime now per test is now also quadratic because we have to, each SNP that we're testing, we have to multiply with this matrix U, which is an n by n matrix times a SNP vector. Yeah. Well, I think I'll do a short pause here. And then
what did you say about the runtime?
I mean, you can answer questions now in the pause. I mean.